All right. In this section, we're going to look at 6.1 normal probability distributions. This is a continuous probability distribution. So in chapter 5, we looked at discrete probability distributions. In other words, you get like 1, 2, 3, 4. Now we're looking at like you can get whole spans of numbers. You can get every number between 1 and 2, 1, 1.1, 1.5, 1 and 3/4, 1.97846. Anything in that span of whatever those numbers are. And we're going to look at specifically normal distributions. But we will also do a problem that deals with another kind of continuous distribution at the end of today. So let's talk about normal distributions. So the normal distribution is one of the most important of these continuous probability distributions, the one we're going to spend pretty much the entire rest of the semester coming back to over and over and over again, is this normal distribution. And this is what the distribution looks like. It has this shape. It's the mean is right in the middle. It's symmetric on both sides, and this mound shape. So here is the equation for this, and you might recognize some of the symbols in this equation. Sigma, the standard deviation of the population, mu, the mean of the population that we're looking at. There's pi, there's E, the natural base or Euler's number is in there. This formula, we're never going to use in this course. Don't freak out. I'm just putting it there just so there is a mathematical model we could set up to do this, but we're not going to be using that formula specifically. Everything we're going to use is going to be related to charts and things, and we'll just refer to those. And yep, there's the mean is set up right there. And there's other features about like standard deviation that we're going to see in this population. Okay, so that's called a normal curve. And here are some features of it. It's bell-shaped with the peak at the mean. We saw that. It's symmetric to a vertical line through the mean. It approaches a horizontal axis asymptotically. Sorry, having a little trouble with my words here. Which means what happens is it keeps getting, like, think about an asymptote that you would have learned in college algebra. The curve keeps getting closer and closer to that line, but it theoretically never touches it. Now, in reality, if we're looking at average heights of US females or something, there's not going to be anybody 0 inches tall or whatever. So, there sometimes it'll cut off on one end or the other, but theoretically it keeps going on forever. The inflection point or transition point from when it's like you think about like in the middle of the curve, it kind of does this, and then on the ends it kind of does this. So it like comes like this and then it curves. That happens at the mean plus the standard deviation and the mean minus the standard deviation. So as soon as you can look at the curve, you can kind of see where it changes from this kind of curve. That's when you hit a standard deviation. That could be a way graphically you could figure out what the standard deviation if you already had the graph to look at. And then the area, and we're gonna see this over and over and over again. We're gonna keep coming back to the area under the curve is 1. And you think about when we talk about probabilities always have to be between 0 and 1. So if you said, what's the probability of getting any of these values? If this curve represents probabilities, then it would come out to be 100%. All right, so here's a slightly more detailed picture here, properties of this normal distribution. Again, you have the highest point of the curve in the middle, and it's a curving downwards. You have those inflection points at 1 minus the standard deviation and 1 plus the standard deviation, and that's where it's changing curvature from a downward cupping into an upward cupping. And it goes asymptotically left and right that way. So there you go. So what I want you to do is pause the video and go and do problems 1 through 4. And then come back to the video once you've completed those. Okay, so I assume you've done those problems. We're going to go to the next part of this section. So if you remember way back, let me kind of jump back here in my textbook. Back in section 3.2, you were probably introduced to Chebyshev's theorem, and it talked about how you could know certain amounts, like 75% of the population is always between the mean minus 2 standard deviations and the mean plus 2 standard deviations. It doesn't matter what distribution you're looking for. That's pretty powerful. You know, it doesn't have to be any kind of set pattern. But when we're looking at normal distributions, we can get more exact because we know that this is normal. It has that mound shape. It's symmetric around the mean. And in fact, one thing sometimes people don't realize, the mean, median, and mode for a normal distribution are always in the same spot. And when you start skewing left and right, the mode stays at the highest point, but the other ones kind of start staggering away from there. So Chebyshev's was based on those minimum percentages, and it could be higher. And in fact, it's going to be higher for the normal distribution. So for normal distributions, we're going to use what we call the empirical rule. And what the empirical rule says is that 68% or 0.68, if you're talking about probabilities, fall between the mean minus 1 standard deviation and the mean plus 1 standard deviation. And I put the ones here just to kind of overemphasize this is 1 standard deviation. Chebyshev's doesn't start until 2 standard deviations for those basic values. Approximately 95 of the percent fall between 2 standard deviations. Now for Chebyshev's, that was 75%. Here we're saying there's 95% within 2 standard deviations. So, you know, most of your data that you're going to have is going to be between those 2 standard deviations. Within 3 standard deviations. Now remember, there's only this 95%, that's only 5% left. You get up to 99.7% of the data would fall within 3 standard deviations if it was a normal distribution. And then that leaves you 0.3%, 0.3% on either side of that. Again, remember when we talk about probabilities, you always refer to those between either as a proper fraction or a decimal between 0 and 1. You don't use percentages for probabilities. All right, so here's how that breaks down. Here's the area under a normal curve. So again, you had 68% between 1 standard deviation above and below. That means you have, since it's symmetric, you got 34% to the left, 34% to the right. And then you get that additional amount. You got another 13.5% left and right. And then you got another 2.35% left or right. And then you got that last little bit out to the side there. Again, these are showing percentages, but when you talk about probabilities, decimals or proper fractions. All right, so let's look at some example problems here. We're gonna do some work here. What percentage of the area under the normal curve lies to the right of mu? And again, mu is the mean, remember? So this should be a super easy answer. If the mean is in the middle, that means half of this information is to the right. What percent? So this is specifically asking for percentages. Let me turn on my little tablet here. Let's see if I can do some writing. It's gonna let me write. Yeah. So 50%. So this is looking for percentages, 50%. What's the next question? Between 2 standard deviations below and 2 standard deviations above. So we go to that. That sounds like an empirical rule. We'll go to our empirical rule, and that was 95% for that. To the right of the mean plus 3 standard deviations. Well, there is 99.7 within 3 standard deviations. You think about it, you got the mean, and you go 3 standard deviations that way and 3 standard deviations that way. And you got all this. This is 99.7. That means you have some here and some here. And the question is asking, how much is here? Well, if we take that 100% minus that leaves us 0.3%, but that's both of them. So you got to divide that by 2, and that gives you 0.15%. 0.15 of 1% is above 3 standard deviations above there. All right, so moving on. Let's go ahead and I'll have you do problems 5, 7, and 9. And again, pause the video, do those problems. When you get them done, come back. Okay, so I assume you've done those problems, so let's move on to the third part of today's. Third part deals with control charts, and then we're going to talk about that other distribution as well. So control charts are a way of kind of charting out data to try to see if the data is in control, if things are happening how they should happen. So think about if you're running a factory or something, you're filling, I don't know, laundry detergent containers. And what you want to do is you have a set amount, you're going to fill it up to, and it's not the top. There's always like when you open it, there's always like a little gap. But why do they have that gap? They're trying to cheat you? No, because there's some variance there. And it's going to be sometimes it's going to be a little bit lower, it's going to be a little bit higher. Some things clump up in the squirter that fills the container, or maybe it flows a little bit better this time. Maybe it's hot, temperature can change that, the viscosity of this things. So there's some variation. So what we'd want to do is we want to keep it around that value though that we set. If this container is supposed to contain 32 ounces, we want to keep it around 32 ounces. Sometimes maybe a little bit higher, sometimes it'll be a little bit lower, but it's always going to be kind of right around there. We don't want to get too full. We don't want to overflow. Same thing. We don't want to, leave it really empty. You don't want to have that Dorito bag that snack bag that only has 3 chips in it. It's all air. We don't want that to happen. Everybody gets grumpy about that. So we kind of have to have that kind of in there. And we want to know when things get out of control, we got to stop things and check it out. So I'm going to try to give an analogy, and I don't know if this analogy is going to work. Maybe it does. It's just kind of a way that it just kind of clicks for me, but I don't know if it will for you. What I want you to think about is imagine you're walking through the desert. And you want to kind of get a good look around. And so you want to stay on top of a sand dune like this. And you want to just walk along the top, just stay on the top. Now, realistic, ideally what would happen is, you'd be here, and you later on you'd be still on top of it in exactly the same spot. And later on you'd still be on top of it. Exactly. But realistically, that's probably not going to happen. You're gonna walk and you're gonna like slowly start kind of going off to one side, and then you'll have to course correct, and maybe you go too far and you get off to this other side. You just keep walking and you're trying to stay on top of there. But how do I know kind of I've gotten off the dune and I can't really see anything? Well, what if I end up way down over on this side, far away from the peak too long? I haven't got up there. I'm looking for an oasis to find a drink or something. I don't know. And I'm getting too far away from there. So I'm drifting. So what I want you to think about is that if we did a cross section, we were to come down and slice the hill here, this dune, it would look like a bell curve. In fact, that's how they made bells a long time ago. They take sand and pile it up, and they put the hot metal over it, and that's how they would make a bell. So this would be like, do a slice, it would look like this bell curve that we're looking at, this normal distribution. And then this control chart is kind of like that top view, so here I am, this is like the top of my head. You can kind of see my arms sticking out here as I'm walking, and maybe I'm over here and my arms, I'm sticking out over here, and here's my head, I'm sticking out, so this is a top view as I'm traveling down this dune. And when I get too far down the dune, from the high peak, I start, I can't see anything. I got to get back and course correct here. And we're going to know when have you gotten too far off the path there. And that's what these control charts are going to help us figure out. So I don't know if that analogy makes sense to you, but I mean, that's kind of how I think about it, is whether you're drifting too far to one side or the other of the hill, you're trying to stay around the top of there. Okay, so if the distribution appears to continue the same pattern, we say it's statistically controlled. It's in statistical control. So, if you're staying around that mean. Now, imagine if we said the mean is here, but you keep scoring everything over here. Like you're just weaving around there. Well, it really looks like your mean's over here, not here. You need to be around this spot. So at that point, we would say, well, you're not following the pattern. You're not doing the same pattern you should be doing. If it doesn't, then we say it's out of control. Things are not where they should be. I'm filling my containers too low, or this is a real world case. Maybe Subway's, their foot long sandwiches aren't really foot longs. Maybe it's like consistently 11 inches. It's like, well, it's okay if you're like a little bit below 12 or a little bit above 12, as long as you're trying to hit around 12. But if you consistently around 11, that's a problem. And they got sued over that. Just real world situation. All right, so how do we know when things get out of control? And there's 3 ways we're going to define how things get out of control. First thing is you get a data point that is, let's see, can I move this? Is more than 3 standard deviations away from the mean. If that happens, we're just going to say everything's out of control. Because remember, there's only 0.15 of 1% chance you would be in that extreme area to the left or to the right. Or above or below, however we're defining things. So, it's very unlikely you would be there if things were acting like they were expected. So as soon as something goes that far out, we're going to say, whoa, hold on, let's check things out. Things might be messed up. The second way to know if something's out of control is you get 9 data points in a row on one side of the mean. So again, you should be kind of doing this around the mean. You might do a little bit, a little bit more that way, and then, but it should be kind of ziggy zag around the mean. And if it's like consistently on one side, maybe your mean is wrong, or maybe something changed. That's why we would say it would be out of control. And then the third thing that we would look for is if you got 3 points in a row, and any 2 of those 3 fall outside of 2 standard deviations. Because remember, again, 95% of the data should fall within 2 standard deviations. So if you go beyond that, it's okay. I mean, the 5%, it's not that unlikely. But if it happens 3 times in a row, that's very unlikely. Or sorry, if it happens 2 out of 3 times. So you got 3 dots, 2 of those 3 dots are outside of that second one. We're like, that doesn't really make sense. It could be 2 right in the row, or it could be 1's out there, then you come back in a little bit, and then you go back out again. That's a problem. So those are our 3 things. You're more than 3 standard deviations out, or you have 9 points all on one side in a row, never get back within that 9 streak, or you get 3 points and 2 of them are outside of 2 standard deviations, 2 out of the 3. Those are our 3 signals that, hey, things are out of control, and probably want to stop whatever production line or whatever you're doing, go back, see if things, and a lot of times that this happens in production line, they have to recalibrate things to make sure it's okay. Okay, so let's look at 283, page 283, number 12 here. We'll kind of do this together, kind of see how you can set this up. So let me get to that page, and I am in the wrong chapter. Like, this doesn't look like what we're talking about. That's because I went back to Chebyshev, and that is not what we're doing here. All right, so 12A. All right, so there, I'm not going to put the whole table up here, but I'm just going to kind of go through and do this. This has, you'll notice on the bottom here, we have the time. So our X values, if you prefer, are the time. And then on the sides, we have the means and the standard deviations. Now I'm going to look through the problem, and it says each day, the average number of visitors treated each day is 21.7. So my mean is 21.7. And my standard deviation is 4.2. So sigma is 4.2. I'm just going to make myself a little note here, 4.2, just so I know it. Let me grab a calculator here. All right, so now you'll notice on this chart, I did mark 1 standard deviation, but I didn't draw like a dashed line. That's because it doesn't really matter only about 1 standard deviation. You should be in that 1 standard deviation area, but it's not until you start getting into past 2 standard deviations that things become worrisome. So I have it there. I'm gonna go ahead and figure out what it is just so I know it, but it doesn't have anything to do with the signals here, but I just have it for completeness. So 25.9. So take the mean, add 4.2, and then add another 4.2, and that's 30.1. So if it gives above 30.1 2 out of 3 times, that's a problem. Add another 4.2, and if it ever gets above 34.3, that's a really big problem. And now let's go the other way. 21.7, subtract off 4.2. Again, this is 17.5. Don't really care about that. Not a big deal. It might help us plot some points, but beyond that, we really don't worry about that in this problem. 4.2. That is 13.3. Again, if we get 2 out of 3 points lower than 13.3, that's a problem. And then subtract 4.2. And if we ever get less than 9.1, then things, again, we're going to see that's out of control. So here we go. So on this table, the first one, 1 day, let's see, we got 10 days. So 1, 2, 3, 4, 5, 6. I could have spread this out a little bit more, I guess. 8, 9, 10. Right. I could have made that bigger. I don't know. Let's see. So on day 1, we were at 25. And so what this problem is dealing with is emergency health services at Yellowstone Park. I think people who are indigestion, sunburn, or even more serious injuries come and visit. So how many people do they treat there? And they say on average they treat 21.7, but with a standard deviation of 4.2. And so this is a 10-day during the summer, and we're trying to say, is there something bad happening here? Oops, I don't know why I have a dot there. This is my dot. Okay. Next one is 19. So I don't know, somewhere around here. And then, yeah, don't look at this dot. That's nothing. On day 3, it's at 17. So, okay, we're getting fewer injuries. Good, good. Not necessarily a bad thing. 15 on day 4. Okay. On day 5, we had 20. So day 5, we had 20. I don't know, somewhere around here, maybe. On day 6, we had 24. Okay, that's good. I mean, it's not good that people are getting injured, but you know, it's good to know if things are acting in a normal fashion. 30.1, so almost 2 standard deviations, but not quite there. Very close. 8. We had 19, so 19. That's I think we already had like a 19. Maybe is around here. 9 is 16, so 16 is somewhere in this area. 9, right? 16 somewhere in that area, and 10 is 23. Okay, so did this, you know, and I think we connect the dots. Is that right? Yeah, we connect the dots. All right. So da 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 do 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 connect the dots. Hopefully. Okay. All right, there we go. So is this in control or out of control? Well, did we ever get past 3 standard deviations above or below? No, we're in there. Did we ever get 9 dots on the same side of the mean? And this, you know, again, this middle line, that's the mean. Well, we got 1, 2, 3, 4, but we never got 9 in a row. We got 1, 2 over here. We got 1, 2 over there. So no. And then did we ever get 3 dots, 2 out of 3 dots outside of 2 standard deviations? And the answer is no. So this we never actually got past 2 standard deviations. So this is in control. So we're good there. All right, I'm going to write down these numbers because I think we're going to have to do the same thing again, and I don't want to recalculate them all. Okay, so 21.7, 25.9, 30.1, 34.3, 17.5, 13.3, and 9.1. Okay, so we're going to do part B. And my guess is this is going to get out of control, just so we got some variation. So again, it's all the same stuff here. So I'm just going to rewrite those numbers. And by the way, you don't have to label these, you know, mean plus sigma, mean plus 2 sigma, you know, you just want to use the numbers. But you're welcome to put those on as well. You know, that's your benefit. Okay, so it looks like we're going to look at another 10 days. I'm going to try to do a little better job spreading these out a little wider. That's a little bit better. Oh, That's an 8. That's supposed to be an 8. Getting ahead of myself. 9 and 10. Okay. So day 1, we had 20 something. So somewhere around there. Day 2, we had 15. So somewhere around there. Day 3, we had 12. Uh-oh. Danger zone. We're getting out there. We better get out from that area. 20. Day 4, we had 21. Okay, that's good. We're up here. Day 5, we had 24. So I don't know, somewhere around here maybe. Day 6, we had 28. Somewhere around, let's say there. Day 7, we had 32. Uh-oh, again, we're going in danger zone. But now we're going on the other way. Day 8, 36. Don't stop. We know what's happening here. Day 35. Okay, day 10, 37. Okay, connect the dots. Da, da, da. All right, so does the data indicate is in control or out of control? This is out of control. Right. Things are out of control. People are getting hurt all over the place. And explain your answers. Identify all out of control signals, 1, 2, or 3. If you were superintendent, do you think the Yellowstone Park Medical Service might need some temporary extra help? Explain. Okay, so first thing that could be out of control is you ever go past 3 standard deviations, and we did that. In fact, we had 3 values passed. So we hit signal 1, 3 points beyond the mean plus 3 standard deviations, right? So we had that. That's one signal. And then, so this said every signal that comes into play. We also had signal 3. Well, actually, let me count. 1, 2, 3, 4, 5, 6. Yeah. So we also had signal 3, and that was at least 2 out of 3 were beyond. And sigma plus 2 standard deviations. In fact, we had 4. We had 4 out of 4, right? So this is beyond 2 standard deviations. This is beyond 2 standard deviations, beyond. So we had 4 points beyond. So yeah, probably need some extra help. If you have a bad day, you have a lot of people there, you're hurt, okay, you might be a little short-staffed, but if you consistently are short-staffed, you need to bring on some extra staff for that, and that's what that's showing. Okay, so it's not a normal distribution, but this is another continuous distribution, and this deals with problem number 16. Number 16 is a homework problem, so this is going to kind of get you going. Since it's not really directly related to the rest of the stuff of this section, I want to take a special discussion about problem 16. So a continuous uniform distribution is when you have something that looks like this. It's a flat percent. It's not a bell curve. Everything within there is equally likely to occur in there. And we're going to label these the lowest value. We're going to call alpha. We're going to call the biggest value beta. Just like with the normal distribution, the area under that curve has to be 1. So if you were to calculate the area under that block, it would have to be 1. Well, this is what we need to know is how tall. One of the very first things you're going to have to figure out is how tall is this block? And the way you're going to figure it out is you're going to say, okay, this is a rectangle. The way you calculate the area of a rectangle is length times width, or in this case, we'll just say length times height, right? What's that height have to be? Well, to figure out the length, we're going to subtract our highest value from our lowest value. That's how we're going to figure out how long the rectangle is. And then we're going to do a little bit of algebra. And we're going to say, okay, if I know how long it is, I know the area is 1, right? It has to be 1. Let me find a formula for the height. And so if I do this b minus a for my length, I want to get the height by itself. I'm going to divide both sides by that b minus a, and I get this formula. The height is 1 over b minus a. And they tell you this on problem 16. They say you calculate the height using this formula, but I want you to understand why it's that formula. Where did this come from? And all it is just saying, okay, how wide is it? Or what's the length of it? So you subtract the highest value minus the lowest value. That'll tell you how long it is. Then you can divide the area by that and figure out what a formula for the height. So just I'm gonna do an example here. Again, this is not 16 numbers. You'll use the numbers actually in 16, but I'm just gonna kind of explain how to do this stuff. So let's say the lowest value is 10 and the highest value is 130. So I want to figure out what's the height. And so I'm gonna take 130 minus 10. That means it's 120 long. So the height has to be 1 over 120 to be able to multiply those and get 1 as your area. So it's 120 long. You multiply it by 1 over 120. It's going to give you an area of 1. Okay. And then you're going to do a problem or 2 or 3 where it's going to say something like this. What is the probability of getting a value between and 2 numbers? So, again, let's say I'm doing the same problem here that I was just working on. I want to figure out what is it between 40 and 120. So it's going to look something like this. I'm going to look for this red block in the middle here and figure out that area. And that's what I'm doing. The probability is the area. It's a 1-to-1 matchup with that. So I need to find that area of that rectangle. And the way you find the area of a rectangle is you take length times, in this case, height. Length times height. So how do we find the length? Well, we find the length exactly how we did with the other length. We take the high value minus the low value. Take 150 minus 40, it's 65 units long. So I'm going to calculate the area. The length is 65. The height we already calculated is 120. It's going to be 120 all the way across. That's why it's uniform. That's why this is a uniform continuous. So I'm going to multiply those. Again, I could represent that as a proper fraction. For probabilities, remember, we're talking about probabilities. So you can't do percentages. You got to talk about either a proper fraction or a decimal. And let's say I want to round that decimal off, 0.542 is the probability. There's a 0.542 probability that I would get a value between 40 and 105. Okay. Another thing they would ask you to do is calculate the mean. A plus B equals 2. So if I wanted to find the mean, and notice this is, sorry, A plus B, alpha plus beta equals 2. Notice alpha and beta, those are the highest values and the lowest value of the whole set, not this particular 40 and 150, it's the 10 and 130. So, and then the standard deviation of the entire thing, again, beta minus alpha, the biggest value minus the lowest value, and then, or the length, how long it is, and divide by the square root of 12, which I'm not going to get into why that's the square root of 12, but this is 10 plus 140. So the average, that's 140 divided by 2. The average value is 70. That's just the midpoint. You take, all you're doing is averaging your highest and lowest. That's how you find the midpoint between 2 numbers. You just take their average, add them together, divide by 2. And then the standard deviation for this problem comes out 120 over the square root of 12. Don't think that's anything. It's just coincidence. It could be any other numbers. Plug that in your calculator, and I got about 34.6 for a standard deviation. Now, this is not a normal distribution, so the empirical rule would not apply to this, but Chebyshev's would apply to this. All right. One thing I forgot to mention, with discrete probabilities, what we did in chapter 5, you can have, what's the chance of getting 4 successes? Or what's the chance of getting 5 chocolate M&Ms or 5 brown M&Ms out of a whole set of M&Ms? You can have that kind of probability. But in a continuous, where you can get any number in there, if I say, what's the probability? So this one was, what's the probability I'd get a number between 40 and 105? And I could get 40 or 105. But if I ask you specifically, what's the chance of getting 40? that probability is 0. The probability of getting any one number, because there's an infinite number of numbers. So your chance of getting 1 out of infinity is 0. That's why in this, when we talk about these probabilities, it's always going to be in a range of values. In a range of values. What's the chance of getting 40 to 150? So if I say, you know, I want to write this in like a more probability notation. Where's my, oh, there we go. All right. If I want to say, hey, I want to, what's the probability that I get this? Should it be that? Or should the probability, should I say it this way? And honestly, it doesn't matter. It will be the exact same number, because the probability of you getting 40 is 0. You probably get 105 is 0. It doesn't matter whether you include it or don't include it. You got to talk about regions. You don't really talk about individual values. So you can include those ends or not include those ends, and it will be the exact same calculation. It will not decrease the probability or increase the probability at all, just because you're looking for this whole area. And, you know, if I'd like, okay, well, you know, take off 1 out of infinity out of that area, it's still the same number. All right. Go ahead and finish up that assignment. Part 3 is problems 13 and 16. 16 deals with that continuous one. 13 deals with, what did we do? With the, oh, the out of control thing. So, all right. Have a good day. That's the end of the video. And I will